So today I'm going to talk about randomly perturbed graphs, and in this talk, let's say n is a large integer, and G and T and H are all n-vertex graph, and T is a tree. So I will omit this in every theorem that I state. So just like most of the talks in extremal graph theory, I'll start with the Dirac theorem. So in 1952, Dirac proved a theorem which said that if G is a n-vertex graph with a minimum degree at least n over 2, which means if we have a vertex, then there are at least, n over 2 other vertices which are adjacent to the vertex, then G contains a Hamilton cycle. So here Hamilton cycle means that the cycle which covers all the vertices. You can visit all the vertices exactly once and come back to the original point. And then, so this is kind of one of the starts of the extremal graph theory. So when we give some condition, can you find certain substructure? So that's the big theme of the extremal graph theory. And later, let me just, and almost 40 years later, Komrosh, Tarkovsky, there's 1 here and 2 here. Okay. Semoredi. In 97, proved. Yep. Oh, yeah.
Sorry, so what does large mean?
So, okay, so for this, it doesn't need large at all, but other theorem, there are other parameters, and compared to that parameter, n is sufficiently large.
So, okay, so to be clear, what?
Yeah. So for this theorem, let's say the T is a tree, n-vertex tree, with a maximum degree and most delta, which is a just natural number. So when this is given, and say n is large compared to this number, so for given that there exists n0 such that or n at least n0, this theorem holds. So that's what it means. And
what is large delta?
so delta, okay, so this is the maximum degree of a graph in here. So which means that for given vertex, there are at most delta many other vertices which are adjacent to this specific vertex for every vertex. So this means, so maximum degree is bounded from above means it's sparse, and minimum degree is bounded from below means it's dense. So one of the themes in extremal graph theory is if we have dense graph, then we can find the sparse graph inside of that. So that's one of the themes. So when we have this sparse tree, so bounded maximum degree with the bounded maximum degree, and say we have, so epsilon is also a small number. So I will just wave my hand to the hierarchy of the numbers, but what it means is that for given delta and epsilon, there is, n, if n is large, this holds for whatever epsilon and delta. Yeah, as long as it's positive. This is positive and this is positive integer. Anyway, so if we have a minimum degree which has slightly more dense than this case, and then if we have a tree, whatever tree, as long as it is, bounded maximum degree, then G contains this T. So for this one was just one structure, one Hamilton cycle. And here it is more general, I wouldn't say more general, but almost more general structure. Because, cycle is not tree, but it's almost like a tree. So this, we can consider this as a generalization of this. So for whatever sparse tree we have, we can find it in G as long as this is dense. And then, let's say, in the same.
Has the same number of vertices as G?
Yes, all of them has n vertices. Yep. So you can find the spanning structure. And same people, Komrosh, Tarkovsky, and Semoredi, in 2001, improve this so that even if, say, T has large maximum degree, so there is some absolute constant such that C times n over log n is m of that, and minimum degree of G is again same. Then we can find the T inside of G. And then there are more results on more general graphs, classes of graphs. So here it's for trees, and there are more results about non-trees, which are, kind of looks like tree and sparse. I wouldn't mention what those results are because it's, not that relevant to my talk, but there are certain those results. And then all of these results are sharp. So the condition here are sharp. We can easily find the counterexample which has slightly lower degree. Let's say, so for example, if we take disjoint union of two complete graphs, which consists of n over 2 vertices, then its minimum degree is actually n over 2 minus 1. Depending on, how, and it's even odd, but almost like that. For every vertex, there are n over 2 minus 1 other neighbors, yeah. And here, it's obvious that we cannot find any, like, say, Hamilton cycle, because there is no way that you can cross, this bridge. And you can also not find any tree, because trees are connected. And also, not only that, we can also consider something like complete bipartite graph with a slight, say, here we have one more vertex, here one less vertex, then we cannot find any Hamilton cycle. And if we take a T which doesn't have a, balanced bipartition, then also we cannot find any such T. For example, if we have a, tree, something that looks like this, then all the vertices in here should belong to the same part. And compared to the other part, there are much more leaves, so it is impossible to find such things. So those conditions are sharp, and if we go below that condition, then we have a counterexample. So that property of containing that structure doesn't hold. But as we see, these examples are quite specific. So it has this specific structure, and there is this reason why, we cannot, there is space, there are not enough space to do that, or it's not connected. So those examples are quite specific.
So the last two, you mean sharp and epsilon?
Yeah, up to epsilon. Okay. So I don't mean that it is exactly sharp, but yeah. But epsilon could be arbitrarily small, so it is almost sharp.
Right.
Yeah.
Maybe you mean that half cannot be reduced?
Half cannot. So what I mean is that half cannot be reduced. And there are later results that actually this epsilon n is replaced by log term. So actually this is some n plus some c times log n, and this is sharp up to constant, but I will not discuss that, but what I mean is this half is sharp. And then, yeah, as I mentioned, these examples are quite specific. So what we might consider is that what if we consider, typical behavior? So there are these worst case examples, but what if we consider average cases? So maybe those counterexamples are very rare, that most of the, cases are much better. So actually that is indeed the case, because for example, the Hamilton cycle case, it is known that Posa in 76 and Kolshunov. Is it the right spelling? Kolshunov. independently show that almost all graphs with at least, say there is some constant c times n times log n edges are Hamilton cycle. Contain Hamilton cycle. So here, minimum degree is say half n, then it contains at least n squared over 4 many edges. So quadratically many edges. But here it says that even with much lower number of edges, most of them are contain Hamilton cycle. So this can be rephrased that in terms of random graph, language. So it actually says that if we consider random graph, so we put vertices, and for each pair we flip a coin, which comes up head with this much probability and comes up tail with the rest of the probability. And then if it comes up head, then we add edges, otherwise not. Then this model with high probability contains a Hamilton cycle with high probability. So that's the same, those two are equivalent. And then, recently, Montgomery announced that he didn't put it on archive, but he announced that he proved for, say, T is a tree with bounded maximum degree, then G n over, say, C times log n over n contains T with high probability. And then for higher, maximum degree, Krivlevich, what's the spelling? Krivlevich in 2010 show that if we consider G and C times delta of T times log n over n, then it contains T. So T is a tree with a given maximum degree, and you just multiply log n, and then this random graph contains a T with high probability. When delta of T is at least n to the epsilon. Otherwise, this implies that, but here we need to assume this. So that's why, this was proved later because, otherwise it would imply that. So this shows that typically, if we just don't consider very rare case, then typically we can find, this structure even with much lower density. So if we want to guarantee such structure, we need it to be quite dense, but even if it has much lower density, typically we can guarantee. Not guarantee, but typically those graphs satisfy that. Then what are the randomly perturbed graph model? So which is a combination of these two. So in some sense, this considers worst case scenario, and this considers average case scenario. And in randomly perturbed graph model, we combine those two. So in 2003, Bowman, Bridge, Martin show that say alpha is a positive integer, a positive real number. For given that if G is an n-vertex graph with minimum degree ls alpha n, then G union with this random graph. So we have G, and there we add some random edges. So we randomly perturb the given graph. Then this contains Hamilton cycle with high probability if P is, say, some constant times over n. So constant times over n means that we are adding linearly many edges. So as here, this theorem says that even if, because this theorem is sharp, if minimum degree is lower than n over 2, there are graphs which doesn't contain Hamilton cycle. But even for that, if we add linearly many edges, then it typically contains a Hamilton cycle.
And this C is dependent on...
Dependent on alpha and, alpha. Dependent on alpha.
So, can I ask?
Yep.
So these, in the last theorem, you let the maximum degree depend on n.
Yes, in this case, yes.
But in all the previous ones,
No, in all the previous one, those are just fixed number. Yep.
okay.
Yeah. So this theorem, for fixed delta, n is much larger. So it's, so we can assume that there is no dependency. Yeah,
But these statements are all asymptotics in terms of n, right? When you say with high probability, you mean?
yes. Yeah, as n grows, equals to the probability goes to 1.
Right?
Yep, right.
So, okay.
Yep.
So there's a difference between that statement and that statement.
Yes.
And that.
So this, the maximum degree can depend on n.
Okay.
Yep.
That must depend on it seems.
Yes. Yeah, we assume that, right? Yeah, it must depend on that. So this is combination of this Dirac theorem and Posa and Kolchinov result, right? So for Hamilton cycle, and also recently Krivulevich and Kwan, Sudakov in 2017 show that if T is a tree with bounded maximum degree, so again this delta is a fixed number, and G satisfy the minimum degree condition at least alpha n, so alpha is again any positive real number, so which means it is dense, then with high probability T is inside of G union random graph G and P with high probability if P is, say, again, at least C over N for some number C. Some number depends on alpha and delta.
May I ask a question?
Yep.
So here you can save, basically the idea is that, or the claim is that you can save the additional log factor
Yep.
when applying a random perturbation.
Yep.
And am I right that this log factor n log n is also the threshold for percolation that makes the random graph connected?
You mean this, right?
Right.
So yeah, it becomes connected around the, 1 plus log n times log n over n. Yes. So yeah, that you are correct. So that the threshold for random graph being connected is something like 1 plus log 1 times log n over n. Here we have the constant c, but I think for Hamiltonian case it's also 1 plus log n. Yep.
So that's a very tight threshold.
Yep.
Below it's not even connected.
Right.
And beyond you can connect
Yes.
whatever you like.
Yep. Right.
So you're saying the C is about 1?
For Hamiltonian cycle case, yes, C is about 1. Yeah, that was not, relevant to my talk. I just put C, but. And then, I will not mention, I will not write, but recently also Bocher, Montgomery, Palchik, Paulson proved a similar thing for non-tree, but a certain graph with bounded maximum degree. They also find the P.
What is just your T is a subgraph of G union?
So in G, we add some random edges, then we can find the T inside of that. So T is subgraph of this with high probability.
You never delete an edge, right? You only add an
Yes, but it doesn't make much difference. In both models, we can prove the same thing. So essentially, I mean, so in this model we just add, but even if we consider deletion, this result actually implies that it's not so hard. It's quite tedious to actually do that. So yeah, people actually never prove it in paper. They mention that it's trivial, and I also believe it's easily done. I never actually, I mean, yeah, rigorously check, but yeah, but I believe that. So there are several points of view for this, I mean, how to view this randomly perturbed model. So one is that, so we have, okay, so one we can consider is this random graph helps G to contain this, say, T, this structure. So this G alone, we need at least minimum degree n over 2. But if we add some random graph, then that threshold becomes much lower. As long as it's just positive alpha times n, we can do. So we can consider that we can measure, I mean, it kind of shows that this helps this to contain certain structure. And another point of view is that we can think it as G helps this random graph to contain this structure. So here, if you see, the random match we need to add was C log n over n, but now it's just, I mean, so this one was, roughly n log n random matches are needed, but here, linearly many suffice. And here, again, n log n was needed, but linearly many suffice. So it, saves the log n factor. So that's another point of view. And another point of view is we can think it as it measures how locally typical this property of containing this structure is. So what I mean is that we can consider a space of all graphs. So each graph is a point here, and we can give a metric. So if we have two graphs, and from one graph to the other graph, you change one edge, and you can change it to the other edge. The number of edges to change is the distance between them. Then that gives a metric. Then in there, for given vertex, we can consider M neighborhood. Yeah. Which means that for given vertex, the collection of graphs that you can obtain by changing M edges.
Up to M edges?
Yeah, up to M edges.
What is M? Is M?
M is number of edges. So, okay, let me mention. So,
Pairs or?
number of pairs, yep. Some edges you delete, some edges you add.
So N choose 2.
It's some number you choose that's less than n choose 2. Then you can consider neighborhood, right? So you fix a distance, say m, and you can consider a certain point, and you can consider its neighborhood with the distance m most m. And what it says is that for given point, so actually, there is certain distinction between whether you independently, add the edges, or you just fix the number of edges that you are gonna sprinkle. But that doesn't make so much difference. So they are actually same. So it says is that for given point, that point might be very bad point that doesn't contain any property. But if we consider its small neighborhood, then in that neighborhood, most of the vertices are good. Most of the points are good. The graphs are good. So that's another point of view. So that means that property is locally typical at this point. Which I should.
I didn't quite get what M was.
Also, there was distance. How far?
So,
how many times?
So if we sprinkle random edges, then how many random edges are added? With high probability, that's approximately n times n. N squared times p. So there are two models. One model is for each pair, you flip a coin to add an edge or not. That's one. One other is you fix M and you fix the number of edges you want to add. And then you randomly select M edges. But those two models are, there is not much difference in this case.
But so one thing I'm confused about is this random graph is not even connected though, right?
Correct. But there are these edges. This is
G is connected.
G may not be. So G may be complete graph, union of several complete graphs, right? It could be. But if we add that much edges, then it becomes connected with high probability. Because this has linear size.
G has minimum degree condition.
Minimum degree condition.
Okay.
So this has at least, alpha n size. So this is linear size. Yep. So what should I delete? Okay, let me delete this one. Yep.
Okay, so I like this picture about that's a first perspective from the three perspectives you mentioned.
Yep. Yep.
But from the second perspective,
Yep.
that means you start with a random point in a ball
Yep.
around zero,
Yep.
right, the empty graph,
Yep.
and then you shift that to some arbitrary
Yes, right.
point.
Yep.
And so, the set of all graphs and vertices forms a group, right? It's
Yep.
a finite group with respect to edge exclusive, or I'm a computer scientist. What you say? Right. So when you
Symmetric difference, yeah.
Yep.
right.
Yep. Edit different. Symmetric different. Yep. Yep.
Right, and so somehow being a group, the structure should be somehow very similar in different areas, right?
Yep.
And, that's the two perspectives.
Yep. Yeah. Thank you for mentioning that. So one thing I want to mention more was.
Sorry, I did my-
Yep. Yep.
So just about this locally typical. This is just sort of
Yep.
a vague notion, or are you sort of defining what it means to be locally typical in terms of the kinds of?
So no, this is just vague notion. That M certainly depends on each theorem, right? Yep.
So can I
Yep.
make one more
Yep.
comment / question?
Yep.
So this minimum degree condition
Yep.
says that really you can have P in in the random graph setting approximately 1 over n, right?
Yeah. In this case,
Linear
yeah.
order for
Yep.
that minimum degree condition.
Yep.
And you're only adding again a 1 over n proportion. So even the fact that this is connected seems surprising.
Wait, could you say again? So that part. But what did you mention about this G again?
G can be as low as P of order 1 over n without.
No, this alpha is fixed number.
Right.
So it's
you just have.
Yep.
Okay. Sorry. The minimum. Okay. Sorry.
Alpha times n. Yeah. N.
Alpha times n.
Yep.
Oh, sorry.
So regarding the third point of view, I want to mention that there is some analogous concept. In computer science, CS. So it's called smooth analysis by Spearman and Tang. By Spellman and Tang. I think it's 2003. So essentially what they did is they answered the question of why simplex algorithm is, efficient in practice. So theoretically, everyone know what simplex algorithm is, right? When we are given linear optimization problem, this is algorithm to solve them. But theoretically, it could take up to exponential time. But in practice, it usually, works in polynomial time. So what they show is that once an input is given, solution is given, and if it's slightly randomly perturbed, then its expected running time is polynomial. So in practice, even if some bad input is given, in nature, I mean, there are some noise and it might be slightly perturbed, then, I mean, usually, with high probability, it can be solved in polynomial time. So, that kind of is very similar concept as here. So, even if worst input is given, if it's randomly perturbed, then it satisfies this property. So, if you see, we have these three theorems. Hamilton cycle, bounded degree tree, unbounded degree tree. And here, random graph, Hamilton cycle, bounded degree tree, unbounded degree tree. And then here, for randomly perturbed, we have Hamilton cycle, bounded degree tree, and there is no unbounded degree tree. So, that's our result. So we can ask the same question. So what if maximum degree T of T is not bounded by this number, if it's growing as n, growing with n, then what would be how much P do we need? So again, for the given delta, which is depend on n, and let's say T, this is delta, so maximum degree of T is delta, and minimum degree of G is say alpha n for alpha given positive number. Then we are interested in P. We want to find the what's the smallest value of P such that this holds with high probability. So that's the question. So let's consider some example and try to guess what's the correct number. So first, let's consider this tree. So let's say this has degree roughly n to the 1 over say k. Some k is some integer, positive integer. And this also has degree roughly 1 over k. And we keep go until the number of vertices is n. We can consider such tree. And let's consider we are embedding them into, say, this disjoint union of two complete graph. So 2. This is, say, n over 2, n over 2. And then we add GMP there. So we assume we add some random edges. And GMP with high probability, this is approximately NP regular, right? So every vertex has degree, in their degree is almost NP. Then, if we want to embed this into that, then we can actually try to compute the lower bound of P. P needs to be at least something, then that kind of gives us the lower bound. So one property of this is that if we just if we just embed this into here without help of this, then every vertex must go to one part, right? It can cross to other part only when we use random edge. So let's just say this vertex is embedded to say this vertex. And then, at most NP edges out of this can be embedded by using this random edges, and rest of them must be just embedded to same part. So let's say this and this are embedded by random edge. Then the proportion is delta over NP. So out of these edges, only delta over NP, up to some constant, that many proportion can cross And then this next level, again, delta over NP from that can cross. And so in each level, that much can cross. So approximately k times, NP over delta proportion of every vertex can cross to the other part. And in order to be able to embed that, this needs to be at least n over 2. Otherwise, more than n over 2 vertex would be embedded to here, which is contradiction. So this should hold. And then, wait. So here, say delta is, so here NP is at least half delta. So let's just forget every constant. So NP needs to be at least delta, up to constant. And delta is here, n to the 1 over k. So if we draw a graph, not the graph with vertices, but this, plot. And let's put here log delta over, say, log n, approximately. And here, let's put log np over log n. And here, this is 1 and half, say, 1/3, 1/4. Then, that shows that in this case, this is lower bound. And in 1 over k case, this is lower bound. So let's just say this is y equal x line. Then this point, this example gives us this point as a lower bound. And because it is monotone, this is a lower bound for, our analysis of P. So if we know this number, then we kind of know, what P should be. And this is one lower bound. So this should be monotone, and it has this lower bound. Then what would be our good guess of the answer would be? So either this or this are natural candidate. And let's consider another example. Another very similar but a bit different example. So again, we consider this union of complete graph. And then we consider this tree. It's almost similar, but slightly different. So these vertices has degree almost delta, whatever delta is we take. And here again, delta. Up until to everything, it is almost delta. But this one has degree n over delta k. Let's not write it this way. It's odd integer close to n over delta to the k. So this being odd integer is important because, so assume this vertex is embedded here. Then, however we embed this, its neighbor, the number of neighbors embedded here and here must be differ by 1. So that means that out of this chunk, one more chunk should be embedded to one part. Let's just assume that this is A and this is B. Yeah, one more part is embedded to A. Then we need to, each chunk contains roughly delta to the k many vertices. And at least half of them should cross to the other side. Again, this GMP is almost NP regular. So by using this random graph, we need to cross at least that much vertices. Then again, here we can do the same analysis. How much we can make it cross? So out of this, almost MP. So that the fraction that we can make it cross is delta over MP times some, say, K, but let's just forget the constant. So out of that, and most that, out of that, and most that. So if we do everything, then again, this fraction, this number, times some constant can cross, and that should be at least half times delta to the K. Then from this we can see that the P is at least, say, delta to the K plus 1. So forget the constant, then n squared. From this, what we can get is this lower bound. So it's quite interesting that, other cases, compared to the random graph case, we save log factor, right? But here, the behavior is quite different. So if we save log factor from Krivulevich result, then that's just this line, the y equal x line. But it's quite different. Actual answer is combination of these two. That's the answer. So at certain range, even if delta increase, the P, same P would work. But at some point, it doesn't start, it starts not to work, and then it catch up the, this line.
For this specific example, lower bound.
Yep, it's actually the best.
It is.
Yeah, so it shows that, in this case, the second example gave us the lower bound, and then our theorem actually shows the upper bound. Yeah, so that is exactly tight up to constant. And then for this range, first example shows the lower bound, and our theorem shows the upper bound. So it is tied up to constant. So actually, our theorem is the theorem with Yost and me. It's not submitted yet. So for K integer and alpha, which is positive real number, say there is M and N0 as follows. Say N is bigger than N0. Then, as before, G is an n-vertex graph with minimum degree at least alpha n. And T is an n-vertex graph with its maximum degree is at least, say, n to the 1 over k plus 1. And at most, minimum of n to the 1 over k, or n over m log n. So again, our theorem goes up until to m over log n. And as soon as we get out of that, there is an example that even, okay. Where is it? Yeah, I deleted all. So if we go above that, it is trivial because P has to be, at that point, has to be constant. So even it has to be, so let me correct myself. Even if P goes to up to constant very close to 1, we cannot guarantee to find the T with high probability, unless it is 1. 1, then we can obviously find. But any, strictly smaller number, we can never find the, tree with the maximum degree, say, n over log n times some constant. So, this is natural to have that upper bound. Then, we can find T in this randomly perturbed graph with high probability, where T is maximum of either n to the k over minus k plus 1, which is this part, or delta to the k plus 1 over n squared, which is this part. So let me mention some proof idea. So we use some ideas. One idea is that if, say, F is a forest, say, almost spanning forest, and then F embeds into this GMP. If delta of F is big O of NP. So I mentioned that this random graph is almost NP regular. So if we have a forest which is not spanning, almost spanning means that the number of vertices n here, and here say number of vertices strictly smaller than n, 1 minus epsilon n for some positive epsilon. Then we can find the F in G. And then if it is spanning, then we can find this if this times this is say big O of NP over log n. So if we have additional log factor in the P, then we can even find the spanning one. And then third fact that we use in our proof is that the balanced per regular graph has a perfect matching. So what it means is that here superregular graph is some sort of graph which satisfies certain pseudo-randomness conditions. So as we know, the random graph satisfies certain good conditions. And even if some graph is not random, if it satisfies certain conditions that random graph satisfies, then it shares many good properties with the random graph. So those graphs we call some pseudo-random graph. There are several concepts of pseudo-random graph, but one of them is the superregular graph. And this superregular graph is actually bipartite graph. So if we have this superregular bipartite graph, then we can find the perfect matching in there. And this fact is useful because if, say, we want to embed this star forest into, so this star forest is some part of T. Inside of T, we have this star forest. And then inside of G, we have this V1 and V2 and, say, superregular graph. And then assume we have already embedded the centers. And then now we want to embed this leaf. Then what we can do is, for this each vertex, we copy this vertex into, we duplicate this vertex into 3 vertices, and say that this vertex and these vertex have same neighborhood in here. And this vertex we duplicate into 2. This vertex we duplicate into 3. And then we consider this graph. And if this graph is again superregular after this duplication, then we find this matching. And then we go back. So go back means we merge them together. Then we get this tree so that we can actually embed it into here if this is some superregular. So that's quite useful in embedding these trees. So what we did in the proof is that one good thing about this pseudo-randomness, this superregular condition, one good thing is that, so as I mentioned, if we have that condition, then we can find many useful structures. That's one useful fact. And the another reason why it is so useful is that whatever graph we have, we can always partition them into bounded many parts, and each parts are superregular. So no matter how large the graph is, or no matter what graph we are given, we can always partition the graph into bounded number of vertices, all have the same size, so that these bipartite graphs are, most of them are superregular.
Is that the regularity lemma?
Yeah, that's the regularity lemma. So, in proof, what we did is first we apply the regularity lemma to G. So remember that we have this T, and we want to embed that into G and G and P. So we apply the regularity lemma to G. And then by playing with it, what we can do is we can partition all the vertices into this superregular pair. So we can distribute all the vertices in this way. So they form a superregular pair. They form a superregular pair. They might not be balanced. Actually, if in the Komlos's and Sarkozy-Semorez's proof, without random graph, if we have a minimum degree at least n over 2, then we can do this with balanced part. And then by using that, they could be able to embed it without help of the random graph. But with lower maximum degree, or minimum degree, we cannot do that, but still we can do it with the unbalanced one. And then, assume we have this T. What we do is for each vertex with high degree, let's not put it that way. So in this tree, we designate some edges. We color some edges with red, and let's say we embed these red edges by using random edge, and the rest of them using edges in G. So we pre-decompose that, so that this red edge only form a tree with not so much maximum degree, because random graph is almost NP regular. So as long as its maximum degree is not much bigger than NP, we can actually embed them into there by using only random edges, as long as they are not spanning. And then what you do is we resolve that, and the rest of them we decompose them into star forest. And then each star forest we embed them by using this superregularity. But there are several issues. One of them is that assume we designate these red edges. Then if we want to embed these white edges, then we cannot embed this star until we embed this, because the center must be embedded before. So we have to embed this. So there are many rounds. And one thing we need to do is that after embedding certain vertices, say in this manner, then rest of them needs to be still superregular. And then embed something, and rest of them needs to be still superregular. So if there are too many rounds, that's very hard to keep track of. But instead, what we can do is not take these edges, but if we take these edges, then after embedding these random edges, they form a star forest, and their centers are already embedded. So we can actually embed them at one time. So there is this difference. So depending on how we color this, random edges, how we can embed later changes. So by decomposing into this T into several, say, so, it doesn't mean anything, but several graphs which are colored by red, which doesn't have much maximum degree, and graphs which are star forest, and then they form this structure. So, the center of, say, F'2 are either leaves of F'1 or leaves of F1. So we embed that. So we iteratively embed that. When we embed the random edges, by using random edges, we distribute it well, so that at next time when we embed this star forest, we have almost right amount of vertices centered here and here and here, so that all the superregular pairs are getting reduced. The sizes are reduced by the same ratio. And then at the end, we resolve these two special parts of the tree, and the does the function of making the number of vertices, right? So everything is asymptotic now. So at certain point, because T and G has the same size, at certain point we need to make it exact. And so here, this plays the role of, making the number of remaining vertices are exactly same as the number of vertices waiting to be embedded. And this, is the last piece, which are not too, which has still, small bounded, small maximum degree. And then we show that the superregularity are still preserved. And at the end, we find this perfect matching, which gives us the exact structure. So that's the some large picture, overview of the large picture of the proof. So I hope, this kind of gives you some idea of how to, use this regularity or pseudo-randomness in, graph embedding algorithm, graph embedding problems. So I would stop here, and if you have any questions, ask me.